Okay, let's get started. So, several announcements before the class. First, there is no in-person class this Thursday. I will be out of town, so there will be like maybe 3 classes will be moved online this semester, and this Thursday was the first one. So I plan to offer that class Friday night, very late. So I will be streaming the class, but you don't have to attend because it's Friday night. So you can watch the video later. I think the content in that class will not be in the midterm. So we can watch that next week. So next week, we will have the midterm, which will be for both classes, Tuesday and Thursday. So each one, you will have 2 challenges to solve. So as long as you understand the homework so far, this week there will also be homework. You also should finish the homework before the exam, because preparing for the homework will help you prepare for the exam. So there will be 4 challenges in total. Each day you need to solve 2 of them. Then I will be out of town next week. And I have a postdoc and PhD students coming here. So both of them have been my TA for this class. And they will be here to give you some hints to help you. I will tell them what kind of hints they can give, what they cannot. But my intention is not to fail anyone in this class, obviously. First of all, if you do all the homework, you get all the points for homework, you almost pass the class, right? So, and the homework part, I'm trying to help everyone so you understand everything, so you can get the full scores for the homework. Then the midterm and final, we will give some hints, but cannot obviously give you the spoils directly. Yeah. So they will be help to help you. Okay, so. So last class, we talked about stack cookies, stack calorie, shadow stack, and several other differences and how to bypass them. So today we will keep talking about differences. In particular, we will talk about address space layout randomization and a firewall at the system core level called Seccomp. That's basically a firewall system at the system core level. So everyone is already familiar with the firewall in the network side, and this one is at the system side. So before the class, we just turned on the address space layout randomization on our server. It was turned off in the first several weeks. So far, all the challenges you have been working on, we disabled a system level protection, which is called address space layout randomization, ASLR, and we just turned it on. So this has been a feature in most of our machines since 2001. This is another approach, an indirect approach to slow down attackers, but it doesn't solve the problem. That's why in this class, we are going to exploit some vulnerabilities, even if we turn on ASLR. So it started as a Linux patch back in 2001, then OpenBSD OS picked it up in 2003. The Linux user space has it in 2005. Windows also introduced this in 2007. So now almost all of our devices, as long as it's CPU based, it's microcontroller based, not CPU based, microcontroller, microprocessors, they are both CPUs. The microprocessor based, like your phone, your laptop, servers, those kind of high-end computers, as long as they have an MMU, they all support this address space layout randomization. It is not well supported in some very low-end IoT devices, embedded devices, especially those without an MMU, memory management unit. It's still possible to support this, but it will be much more expensive in terms of computational cost. Slow down very much. So what is this feature? Address space layout randomization. So far, when you exploit the software, to find a vulnerability, you want to give your control back to your share code. You want to return to a specific function. You need to know the address of that function. You need to know the address of your share code. Even though there are some tricks we are playing to make you, you don't need to know the exact address of those. Like we put a lobsled in front of that. You still need to know relatively where that address is, a rough idea where that is. So if you want to return to a particular function, then you have to know the exact address, right? So that we have return to libc attacks. So the defense here is very simple. The attackers, they need to know the address where they jump to. Then we randomize that address at runtime. So every time the attacker run a new program, attack a new program, they will have different address, right? So we randomize that. So the attackers will not be able to know where to jump to. But like I said, there are chances you can guess the addresses in multiple, many times. Like what we did in the stack clarity one, right? We were guessing the stack clarity. So if there is a program that forks other program, the address space will stay the same, and we can guess their addresses. We've got an unlimited opportunity to guess. So this is still not a perfect solution, but it has been deployed and it has been useful. It slows down attackers. So that's why we are starting this. To make this happen, there is another concept. It's called related concept. It's called precision independent executables. So basically, it's a piece of code or an executable of many pieces of code. So those pieces of code, they can be executed at any place, okay? So that's why they're called precision independent. So if you only look at it at the instruction level, most instructions, obviously, they are already precision independent. Let's say you have an instruction of move 1 to register year X, or exclusive year X with year X. Those instructions obviously are already precision independent. No matter where you place them in the memory, they will execute correctly. But there are other instructions or sequence of instructions. Their location matters. For example, there is a memory location to year X instruction, and that memory location is not an absolute address. It's an offset of the current instruction's address, right? Many instruction set supports instructions like this. Intel also has similar instructions like this. Even jump, the jump instruction would take an offset, like 1 byte or 2 bytes of offset, instead of taking the full absolute address. So those instructions, obviously their location, the position matters because it's related to other resources in the memory, right? So then if we want to move the code around, we want to randomize the code to different places. So far, they are at a fixed location. That's why when you want to find in the homework, when you try to find the location of print flag or try to find the location of print secret, you just debug. You use GDB, you use P to print out the address, then you get the address. Because whether it's in GDB or not, they have the same address. But with this defense feature, ASLR, they will have different address. Every time you run that, it will have a different address, right? So if you want to enable this feature, the very first thing you need to do is to make sure your code, they can run at any place, okay? Not at, so the compiler has to compile them in a fashion that they can run at anywhere, okay? So they are not supposed to use, they can still use relative address, but when they use relative address, we need to get a runtime base address for that relative address. And this is called the PIE or PIC. So when you compile those programs, you need to give a compiler option. I want to compile this is a PIC or PIE. So the idea of address space layout randomization, I already said, it's just randomize their locations of everything. For example, this is a figure we saw in the very first class. And this is a 4 GB memory map of a Linux program. So before ASLR, usually what we do is we put the code segment at the very low address. Obviously not 0, because 0 is reserved, it has special meaning, right? In C programming, null pointer has a special meaning. So it has a very low address. Then after that, we have the data segment, we have uninitialized data segment, we have heap, we have libraries, we have stack, and kernel, right? Then in those libraries, regions, maybe we even have some rules to place those libraries, right? So the idea of address space layout randomization is very simple. Instead of putting the text, data, BSS heap, whatever, at a fixed location, every time we run a program, when the loader loads the executable from the file system, loading that into the memory, we are going to load them at different addresses. We can even break the same section like .text, the code section, into smaller pieces and scatter them in the whole address space. So they will be at random places. Okay, that's the idea, right? Not necessarily we are going to use the full entropy of the address space. That's why, because for performance reasons and other reasons. So let's say one example here. This piece of code will only print out the address of some symbols in this executable. The symbols here include global variables, local variables, function names, those things. So we have I do not say the main function. Oh, this is the main function. The main function is very simple here. We just print out the address of different things. We first print out the libc function addresses. Printf is at which location. Memory copy is at which location. The distance between printf and memory copy. The address of system is at which position, and the distance between printf and the system. Then we print out the module functions. The module function means the functions developed by the developer in this particular program, not in other libraries. So we print out where main is, add is, the distance between main and add, the subtract function there, their address. Then we print out the global variables address, and the initialized global variables address, and the global variable initialized and uninitialized global variables distance. We also call the function compute, and in function compute, we print out the local variables address. They will be on the stack, right? And if we run this program, so before we turn on ASLR, the system you have been using so far, before start of this class, you are supposed to get the same address for everything. No matter how many times you run this, you're supposed to get the same address. So I just asked the TA to turn on ASLR. So for any other programs you have been hacking, if the program prints out the address, you can try the same thing. It should have a different address line. So let's run this. Maybe we will have 2 windows that will be there. Okay, we run the same program twice. And you can see that now the address space is randomized for those 2 instances of the same program. Left-hand side, we have printf at F7 B472. Now the new instance has B862, right? So you can, however, the distance between printf and memory stays the same, you see, which means for printf and memory copy, obviously they belong to the same library module or whatever, and that library module is randomized. The location of that is as a whole. So even if that piece of module is randomized at different places, but inside them they keep the same offset, the same distance, right? You can see from here. Then the system has a different address as well, and however, the distance is also the same. So that means maybe the whole C library is one big piece, right? Then the module functions, you can say their address are also different. This one is 63, this one is 62. But how many bits of difference here? So for main function, we start at 56, then 62 here is 63, so it's 62 to 63, a little bit change. Then this byte is different, then this half byte is different. From here it looks like maybe only 2 bytes of difference. So maybe only 2 bytes are randomized, okay? The middle, those 2 bytes are randomized. So if 2 bytes are randomized, then we are only providing 6 bits of entropy. So if this program is can fork other programs, then it's very likely we will be able to do a brute force to guess. It's just 16,000 different cases. Then you can see the main function's address, the add function's address is a constant offset, B0, which means that piece of code, the part that developer developed, this is also a big piece. We do not, at least on this server, the ASLR we're using on S server in the kernel, they do not really randomize those parts. The loader do not randomize that one. Then let's say the global initializer variables also have different address. But it looks like the entropy here is also just 16 bits. The offset is the same. The uninitialized variable, the same thing, maybe 2 bytes. Even the stack, right? The stack address, they're also slightly different. So this is basically how ASLR works. This is implemented in the kernel. The loader will also need to do something. So how many of you took operating system class before? And there is one of the books that is classic to teach operating system. It's from MIT. It's the x86 book. Yeah, so you guys did the x86 book. So, okay. So in the x86 book, actually, in one of its chapters, I think it's memory management, and the homework was to implement ASLR. on top of x86. So if we go to the 64-bit version of the same code, so if we go to the 64-bit version, let's say how many bytes of randomness we get here. Looks like we get more, right? 7E to 6, 5, and we have at least those 3 bytes. 1, 2, 3. So it looks like we have 3 bytes of randomness here, right? The address space is 8 bytes here, so 3 bytes of randomness is not that big. But in 64-bit systems right now, we're not really using the fully 64 bits for the address space. We're using like 38 bits or 39 bits so far. Right? So that's why we only get 1 more byte of randomness in 64. So any questions so far? So to compile those programs, you have to compile it position independent, which means you do not know their absolute address when they are in storage, in rest. If we do a NM on those programs, you can see that all of their symbols, they only have an offset address, no matter 32-bit or 64-bit. So it starts with a very low address. It's obviously not the real-time address, the runtime address. That's just the offset. But for some other programs we have been hacking so far in the class, if you do an NM on them, sometimes you find an absolute address. So the loader is supposed to unlearn that and load those variables or symbols to that particular address. But for those ones, because it's the loader and the OS job to decide at runtime where they should be loaded. So out of the program, file header, everything, we only have an offset. So we don't really have an absolute address. So when you say something like this, that's one of the features of those PIE programs. This is basically trying to get the current address of this particular instruction. Like I said before, if this is not a PIE program, some of the functions, some of the instructions, they know at compile time, we already know where that instruction is. And we know the offset between this instruction and another resource this instruction is referring to. Then that instruction only needs to use a relative address, and the relative address will be much shorter, right? Maybe 2 bytes, doesn't have to be a whole 4 bytes or 8 bytes. Then if we want to keep that piece of code, then what we need to do is we need to get at runtime, we need to get where that instruction is, then add that offset to this instruction. And this piece of code, this function is trying to do that. So here, this function is called get PC thunk AX, which means we are getting the runtime address of the PC, and the PC is basically this instruction or the next instruction. Basically, it's trying to get the address of itself, the runtime address, absolute address itself. Now, after that, we get the address, then we are going to add the offset to that address. So we're getting the address to EX. You will see other functions as well, like get PC thunk.px, cx. Basically, the AX, BX, CX here are the destination to store the address. Then we add an offset to that. So now we really get the resources runtime address. Then we are going to refer to that address like here, right? So here we're actually referring to that. We are reading some value from that address. So this step is critical here. Otherwise, we do not really know the runtime address of that resource. So the call instruction, we can say, it has many different forms. As you can see here, res16. So you use a relative address as the parameter. So when you debug this, when you disassemble this, sometimes you say call a 4 bytes address, right? But sometimes that 4 bytes address is not really a 4 bytes address in the code. The 4 bytes address is calculated by the disassembler. So the call instruction actually, the parameters there are only 2 bytes. But this one can do 4 bytes address. So but you can see many different cases we can use just a shorter address of the offset. So the PIE overhead is not very high. As you can see, we add some instruction there, like that function call. The function call could be implemented in just several instructions, especially in 64 bits. All strings, some resources can be accessed relatively from the RIP. There is instruction to do that. So there is an instruction to do RIP plus something to the move to something. But just 32-bit, we don't have this instruction. So as long as you put, so as long as the distance between your resource and your code, that is fixed, then the whole thing can be moved around. There is not much overhead there. However, in 32-bit, we cannot address using EIP. That's why you see functions like this. Get PC some different registers. And that will bring like 3% overhead because that's a function call and several instructions in that function. Yeah.
So that offset calculated as part of the ASLR wherever that's happening.
The offset actually should be, well, most implementations for now, the offset is fixed at compile time. The ASLR will randomize the base address for different modules. Yeah. But if in this case, if this is a string we are referring to, then obviously the offset between this string and that instruction should be fixed as well. Otherwise, you cannot use this to refer to that string. Because we don't have this instruction. The instruction set doesn't support this. Yeah. So instruction set doesn't support EIP plus something. Yeah. You basically you cannot really dereference from EIP. Yeah. Yeah. You do not have a instruction to directly move something to EIP. So far, what we're doing, right? We are using other instructions to move some data to the EIP. For example, return. Return is basically popping something on stack to EIP. But there's no instruction directly to move something there. Yeah, doesn't exist. So we already say this actually. So with different address, we already saw this. So 64-bit, the same thing. Okay, so how do we bypass this?
This one more thing. So when the OS is calculating the randomizer, it needs to go through the program and find all the offsets and then randomize it, or does it not care about it?
So this is quite complicated. It's collaboration between the OS, also the loader, right? The OS so it's more like the loader will actually load different things. When you do exe cde, the OS will first load the loader there. Then the loader sometimes actually run in the user space. And the loader will make different system calls, like we saw in the very first class there. The loader will make system calls to load different libraries, use a memory map, open, those kind of system calls. Right? So when they do a memory map, when they make that system call, the operating system will give it an address. Say, we are going to map what you are asking to this place. Then that is where the OS can do the randomization, right? Every time you make that system call, the OS will get a random number and place those things in different places. Yeah, make sense? So this is not a direct defense. There are still ways to bypass this. The first way to bypass this is through some kind of information leakage, address leakage. So some vulnerabilities will allow attackers to obtain the addresses required for attack. As long as we get those addresses, we still bypass this defense. Also, some vulnerabilities allow attackers to obtain to access data relative to a particular address. Also, we can bypass this. And also, the implementation, the idea of this is good. However, the real world implementation may not provide enough entropy there, right? We are going to see another particular case, how we can do that. And also, there are some side channels of the hardware for information leakage to help us bypass this. So this is the program we are going to hack today. The main function takes two arguments, ASLR2 and string. They equals vol_foo equals exit. Vol_foo will print out its own address, the function vol_foo's address. It has a local buffer, 8 bytes in Seccomp. We do a memory copy from whatever your input is to the buffer. So here we don't have stack calorie, so no channel stack. So there is a buffer overflow here. You can overwrite the return address of vol_foo then return. The problem here is ASLR is enabled here. Okay. So it doesn't have a fixed address. Then how do we override this? Let's go to ASLR. So if we just put some random input, we get a segmentation fault, and it print out where the vol_foo is, which is at this address. If we run this again, it goes to a different address, right? Our goal is to return to print secret or print flag. Because the print secret here actually just called print flag. There's no parameters, so either way is fine. So how do we get the address of them? Yes, the last byte is always the same, right? Yeah, the first byte is always the same. Okay. In the middle, they will be different. So how do you hack this? So this half byte, this digit is also always the same, you see, right? So that's 4 bits. This looks like this 4 bits is always the same. So the entropy here is actually just 12 bits, right? Sorry. The 6, and this one sometimes changes. Okay, yeah, so this one changes to 5, but looks like it can only have like maybe just 2, not all 4 bits of randomness. Right? Now how do we access? We can brute force this, but brute force this will also be very tricky because so our exploits will look like we have some fittings at the beginning to fill the buffer. Then we will have the address of print secret or print flag, right? The print or secret or print flag, we probably want to have a fixed address. We will have the same address all the time. Then we just keep running this program, right? So it's like buying lottery. You always go to buy the same lottery number, but hopefully it's get drawn here, right? And the chance for that actually is not that bad. It's 1 out of maybe 14 bits, 2 to the power of 14, right? So which be 4,000, 5,000, 4,000 or 10,000 times. So not that bad actually. So it's possible, right? Are there any other ways, smarter ways to do this? Here we have multiple set. So we have the return address. So far, we have been looking at this return address of the whole thing, 4 bytes. Let's break them down. So here is our buffer, right? Then this address, let's say one particular case will be this is high, this is low. The last case, first byte will 56, second will be 58, 58, 9408, right? The vault is at this address. Actually, the vault this will be the address of somewhere in the main, right? So it will not be this address. So this one, we don't know what this is. Maybe even this one, we don't know what this is. This two, probably we don't know what this is. So how do we hack this? Okay. Okay. So the last okay. So how about those 2 bytes?
Right. The first one I think will be 560.
Okay. But it will change, right? Sometimes it's 56, sometimes it's 55 or whatever.
The third, the second byte.
Oh yeah. So this one probably stays the same, but this byte may change, right? But may not be that random. So there are several cases we can try. But do we need to try this? We really need to try this? Do we need to try different numbers for this byte? What if we just leave it there? We do not touch it, right? Then it will have if we do not change this, it will have the randomized address of the somewhere in the main function. And that is probably the same as the randomized address of print secret, right? So it is already on the stack. We just do not overwrite this. We only overwrite the last byte, right? So that's much easier. So then let's check this so we get down. So you can say Wolf's address, the offset is 1408. No, we're not going to Wolf, we're going to activate the main. The main address is 13A9, and after the call to Wolf, this is the call to Wolf. What will be put on is 13 on stack will be 13 FB plus the base, right? 13 FB. Then we want to go to print secret or print flag, and print secret is at 13.8B. Okay, and we already saw that in different cases, the last byte is not randomized, right? The second byte, the least significant byte, this may be randomized. There is a base address plus 13, but print secret and the address on the stack already, part of the address inside main, they will have the same byte there anyway, because the offset is the same, 13. The base is the same, right? So we don't really need to change that. We only need to change the last byte, bypass this, right? So if we want to go to print flag, say where is print flag? The print flag will be a little bit different, because print flag will be 12 AD, which means it will have a different value. It will be 1 smaller than whatever is on the stack. So this byte, if we want to go to print flag, this value will have to decrement it by 1. To decrement this, we need to know its value, but we don't know, right? So, but if we go to print, only want to return to print secret, this one is actually very convenient. We don't care about this byte. We only override this, right? So let's see if it works. We take a look at how big the buffer is. This is oh, I forgot to share my screen. Oh, you are sharing. Okay. So let's say for involve. So here is a memory copy, and you can say year X is at EBP minus 10. So buffer is 16 bytes plus 4 bytes of saved EBP. That's 14 bytes. So after 14 bytes, we have the address, and we only need to override the least significant one, which we are overriding to 8E, right? Yes. So that is how it works. This one takes from yeah, this is from argument. So we 18 bytes of garbage plus some address. Right? We don't really need a full address. If we put a full address, it may not work because we have to guess them. Let's say we guess 56. This one should be 8E, I remember. So if we guess this way, we get segmentation fault. And we are trying to return to this address, but the actual address will be 56610488, somewhere there. Even if we get that, we try to do that again with this. If we do this, it doesn't work either, because for this process, the address has been updated, changed, right? But if we only override the last byte, this should work. Yeah, not working. Which part is wrong?
the board is divided.
Oh, 20, okay. Oh, 16, yeah. Okay, see, so if I only override this, that works. So for the others, we also change to 20 bytes. Right? It won't work. So when we are exploit, in this case, is shorter, smaller, and it works. Let's say oh, this one was so we were close here. Look, we were trying 56, 61, 04 AB. This one is actually 54. We're trying 04. So we were actually only 4 bits off. So if you keep trying, you may get lucky. This one now it changed to B4, but this byte already changes, also changes. So using many other tricks, this is a case-by-case scenario. If you analyze your program, you will find this program may have a information leakage or some other heuristics you can use here to break it. So in this case, this particular program, we actually only need to override 1 byte here. Then we are able to capture the flag. Yeah.
Is it common to not override the last, the offset, the randomized offset is not affecting the final? Like, is that common or is it?
I would say it's quite common because the fundamental reason here is not enough entropy and also not fine-grained enough. You can say we are randomize the whole piece, the libc, the program module. If you break them into smaller pieces, let's say you break them into function level, right? Then so the offset, the distance between different functions always change as well. In this case, we say that the distance for function, they do not change, they stay the same, right? So especially for some low-end devices, if you want to implement this, you need to find places where you can increase the entropy. Then you need to go to the function level. The function level is probably the smallest you can go. I think actually you can go to the basic block level, right? You have you rearrange the basic blocks so the control flow change. That's also possible, right? So you can get more entropy there.
So, you override 1 byte. What's that function? The word.
That's pretty secret. We use the obj dump. Check that. That's pretty secret. Yes. So those 3 bytes, every time they are different, right? But we do not overwrite it. So basically, the original address we have is somewhere in the main function, right? And for that address, the higher 3 bytes are always the same as the address of print secret. No matter how they are randomized, then those 3 bytes will be the same. Because of that, we simply leave them there intact. We don't touch it. We only change the last byte. Make sense? No, 8D is not a guess. 8D is from the obj dump. So from this down, we find that the main function, the return address will be this one. It will be the last byte will be FB, okay? 13 FB. So this 13 will actually be changed because our base address also this byte is now 0. So when we add together, this one will not be 13 anymore. Okay. However, the print secret function, its address is 13.8B, right? So you can say they're very close. One is 8B, one is FB. Okay. So no matter what the base is, when that base added to this address and added to that address, the higher 3 bytes will have the same value. The only difference is the last byte, this byte, 8B. Make sense? So we're changing the return address from whatever 3 bytes and FB to whatever 3 bytes and 8B. Okay. Cool. Any other questions?
Yeah, so basically the reason is that the return address of the initial one close, very close to the
Yes.
print sequence.
Yes.
And their high 3 bytes is the same because they are very close.
Yes.
Okay.
Yeah.
So how can we know the initial?
We don't really know the value of the initial address. We don't know, right?
We don't.
Because runtime is different.
We didn't know the last 1 byte of the sequence.
Yes.
Okay.
So let's say in this case, if you want to jump to return to print flag, it will be much more complicated
You will be like there.
because you need to change 2 bytes.
Not the 2 bytes.
But the second byte, you don't know how to change that.
Oh, no.
Yeah, because the second byte, you know you're supposed to change it to its current value minus 1, but you don't know what the current value is, right? Yeah.
Because the last byte of similar to the byte I three, the last byte of the.
Yeah. Right, what? You can actually it's not that bad because that is just 1 byte, right? So 255 chances, 255 bytes. Right? So let's say, we can take a look. Let's say, let's run this program multiple times, okay? Oops. Run this program multiple times. You can say, here, the last byte doesn't change. This byte change a little bit from 44 to B4. Let's run multiple times. So this digit never change, right? So it's actually four bits of randomness there. So then it's possible for us to do that. Let's say the value is at this address B4. Then let's do an obj dump again. Obj dump. So let's see where value is. Value is at value is at this address 1408. This is the last byte. And its runtime address.
I think you want print flag.
What?
You want print flag.
Yes, we want to print flag in this case. Yeah. So the runtime address value is we saw 3408, B408. So it's something. So which means this bit doesn't change. This digit 4 bits doesn't change. But plus something here to get 3, 8, 6, whatever. Right? Then print. We want to print flag. Print flag is at print flag is at 12 AD. Is at 12 AD, and that. So that one will be 13, right? The some address on the main where we're returning to will be 13 something, but doesn't matter. So okay, so we need to change whatever this byte is to a smaller value, and this bit we already know. this speed will be 2. So this speed actually stays the same, right? So which means we want to go to print flag. The print flag address will be something 2AD, right? So this one is for sure to be 2. So this is what we need to guess. Okay. So what we can do is, it's actually not that bad. Then we maybe just, I would say we just try 1 to 80. Then we keep trying. So there is probably 1 out of 16 chances. Yeah, let's try that. I actually have never tried that. So if 1, then it will be 1 to 80, right? Okay. Let's try. So when it hits, so this value should be what? Should be 1, right? This one should be 1, right? So let's say if it's ever 1, if it's not ever 1. Ooh, yeah, we got it. Yeah. How many times we try? Yeah, maybe. Yeah, almost 16 times. Yeah, so it works, right? So this is literally drawing a lottery. Yeah. Yeah, so this is all you can return to print flag. Any other questions? Good, okay. So there is one more.
Right, giving this in as the last slide.
Yeah.
And it was giving usage because AD is a rate or something.
AD.
I just tried AD instead of like, 4 bytes, I just gave 1 byte.
That doesn't work
Yeah, so,
because when you do that, you are actually returning to 13 or
yeah,
13 or because you didn't change this part. Then you are going to yeah, so we can actually we can find out where that is.
but either way it doesn't work because AD is the running from state to state. So when then
You changed it to 8D, right? 8D,
because print flag
the last byte. Which one?
print flag, not by print flag.
Print flag?
That is not the AD.
Yeah, this one will not work because, okay, let me explain what happens here. When you do that, so originally, the return address will be this, right?
1 period.
Yeah, so you only change the AD, you are going to, where's AD? AD, sorry, AD. You are going to here, right? You are actually returning to this place. So you're returning to the beginning of main function, okay? And obviously that's not going to print the flag and eventually trigger a segmentation control. Yeah. Okay. So so far most of our OS implements this ASLR when we enforce this when a new process is created. And there's a lot of problem as the fork system call, same as the stack query. If you fork a program, that program is not really created by using execde. So everything is copied there. Even the address space was copied there. So for web servers, which create a new process for each request or create a different threads for each request, their address space will stay the same.
That is when the process like finding for it will not have this new item.
because they are using different system calls. Only exe CVE will randomize things. Fork will not do that. That's the implementation. That's why there are people trying to solve that problem. So this paper published in NDSS almost 10 years ago was trying to re-randomize this address space after some time period or something. This is a very complicated problem because imagine your program is running, then you want to randomize things when it's running, right? Very, very complicated stuff. You feel this may not be very reliable, right? And also the overhead may be high, but there has been research on this.
Can be compared with the randomized when the fork is there.
Yes, that will help. That is better than exe CVE, obviously. Yeah. It may be as difficult as this one because a program can make the fork system anytime. Then it already have very complicated pointers to point to different locations. Then you need to randomize it. It's still also very complicated because yes, there is a simpler scenario is you do a fork, then you do exe CVE. In that case, if you randomize that fork, no, in that case, don't matter either. Because in that case, you are doing fork, then exe CVE. After you fork, in fork, you randomize the things, but soon you are going to replace everything with a new image. So that matter, you are wasting your time to randomize things. Right? Yeah, it's a new address. Yeah. Yeah, but you are wasting some computing resources there.
The main fork is you have the copy and write.
Exactly.
You don't get that.
Yeah, the point of having fork is to reduce the cost, make it very fast. Okay, so one more difference is called secure computing mode, Seccomp. So this is basically a firewall. And this is a firewall at the system core level. When we talk about firewall, it means there are some requests we do not allow, right? Some requests we just block it. We do not allow that. It could be a network packet, which is a network request. And we saw that request net packet, we say, oh, we do not take this, we block it. We can have network layer firewall, can have in your local computer, you can have in our routers, and many other places. So this is a system call firewall, which means part of the OS. Whenever an application makes the system call, the OS will decide if this application should be able to make this system call. So this kernel module allows developers to write very complex rules to allow certain system calls for a particular application, disallow certain system calls, and also filter allowed and disallowed system calls based on those arguments variables. If you want to learn more about that, you can just read the manual. We will just show some simple examples of this. So the history of this first developed by Andrea back in 2005, merged into Linux kernel in 2005 as well. And Android has been using this since 2017. So how do we use this? Those are the APIs for this module. The applications can, at the very beginning of the application, or even at runtime, you can set what permissions it can, what system calls it can make. For example, we have been running several different applications, tax different applications. All of those applications, then we have the share code, right? The share code makes the EXE7E system call. And sometimes it makes open system call, whatever. So what if that original application doesn't really need that system call? The original application, the very simple application, we're never making EXE7E, the system call. Then why we should allow this process to make that system call, right? Then we just take the ability off. We have two versions of this piece of code. One version is a very simple one, just do a system call EXE7E being cat, then cat flag. That's it. Okay. So this is the setuid program. So without this part, okay, forget about this part. Well, this is a macro. This is pre-compiling. We can remove this part. We'll only execute a new program and cat a flag. So we will be able to get a flag, right? So if we compile this program with this macro defined, then this piece of code will be also be compiled there. And this piece of code is very simple. It's setting up this Seccomp feature and also add a rule there. And the rule here is do not allow this process to make the EXE7E system call. That's it. Yeah. So first we set up a context. That's just the API of this feature. And we initialize this context. That's also standard. So the key here is add the rule here. The rule here is we are adding, when there is EXE system call, we are going to kill this application. Then we make this effective. That's it. Yeah.
I'm not sure if it's right, but will it ever happen if there's a buffer overflow and we get able to go the right place?
Yes, that's possible. I mean,
But eventually there will be a stack that will be there.
so it's possible that somehow because this and rule, initialization, everything, load everything, they eventually also map to system call, right? This is mapped to the system call to this special module, right? And it's possible you can make system calls like this again to add new rules. Yeah.
But that will always be allowed, but that's the configuration.
I think you can also disable this as well. Yes. So there are ways to attack this as well, obviously. Yeah.
But without mobile system call, it will just change like there's the existing parameter given to that function there. The possibility of changing something like what allow it. Like instead of getting that change the act, you can do another function for that.
So you can see, at least for this one, this is the parameter, right? And this is hard coded. So this will be the code part. So this will not be on the stack. Yeah. For this particular case, probably not. For other cases, maybe you have a variable there, then use that variable, then that's possible. So this is the Seccomp disallow part. Let's do the allow part. So the allow part is very easy. You just can ask the flag, right? So if we do a S-trace, of course, S-trace will not give us the flag, but you can say S-trace, we're just after the EXE. So here we're doing EXE7E to cat. Then after that, when we actually write this, we don't have a permission because we're doing S-trace. So this is the allow one. Allow version, just give us a flag. Very simple. Then the other version is allow. When we run this, you print out bad system call. That's it. So it's blocked. We go as trace here. We go as trace here. You can say first execute this program executing, then this module is setting up the firewall. Like to set up the firewall, the program actually also makes those system calls, and this system call is called Seccomp system calls. After that, when we try to execute the new program, it's get killed, right? So here is not because permission denied. We're not even there. We're not even trying to catch that file yet. When we make this system call to do this, it got killed. This process got killed. So that is basically the firewall to stop this. Okay, so that is the last slide I have today, and we still have we still have 25 minutes. So in this 25 minutes, you guys can start working on the homework. I posted already. So for this week, the homework actually you don't need the ASLR, so we are going to disable ASLR for this week. For next week, for the midterm, you also do not need the ASLR. After midterm, I will enable ASLR for the new homework, which means the homework should be delayed a little bit. Anyway, okay. So today's homework, there is a new challenge you haven't seen so far. So the first 4 tasks, you have done all of those actually. I showed you the demo in the class, except this one. The command line arguments, I didn't really show the demo, but you should be able to figure out how it works. The other 3, I showed you the demo. The 5th task is new. You haven't seen the source code. You need to disassemble this to figure out what the program works, how it works, and to figure out how to hack this one. Okay. So I give you some hints here by the way I name it, right? So if you need to override the return address, I always name it like overflow return, right? If you do not override the return address, you just override some local variables, we just call it overflow instead of overflow return. Right? So that's the hints. So I will also give you that level of hints for the midterm. Yeah, so by the name, you can get a rough idea what this is for. So now I ask the TA to turn off the ASLR, then you can start working on this. It's actually a OS feature. We're turning this off. We are making a system call to the kernel. Yeah, but to make your program run on a machine with ASLR, it must be compiled in a special way, the PIE. Yeah. And for now, it's probably the default way to compile programs. We only have midterm next week.
Next class. you have-
Next class, we are talking about, share code. You need to, in that class, you will develop your own share code based on the share code I gave to you guys, right? I will be out of town, but I said that, I also said that. So it will not be an in-person class on Thursday. Yeah. Yeah, like I said here, I will be out of town, so I will deliver this class online using the office hour Zoom link. And I will deliver this on Friday, 9 p.m. Yeah. So you don't have to, I will be streaming this, but you don't have to be there because it's Friday night, but you're welcome to join. Yeah. Then I will post the video online. Oh, you were not here when I talk about it. Yeah. Okay. So ASR is off now. We can verify that. So where is our ASLR fullback? ASLR. Yeah, it's off. I run it twice. So this one is B65C. Last time I run. The same address, right? But this is a program we ran at the very beginning of the class. Now they have the same address, run twice. ASLR is offline. Yeah. To prepare for the midterm, just to go over the challenges you have done so far and try to understand why it works, why it doesn't work. As long as you understand those, you'll be fine.
How many times?
2 and 2. Each day you have 2 challenges. Yeah, you have about Tuesday and Thursday, right? Yeah. It's open book. You can watch the lecture videos. You cannot use ChatGPT or large language model. That's a rule. You cannot talk to each other, have to be independent. Okay, that's only the rule. Yeah. What? You can Google. Yeah. Yeah. I think it's 150 minutes. It's just the cost. Yeah. In class. So you can Google, but you cannot post the challenge online and ask someone to solve it for you, obviously. Yeah. Okay. Yeah.
How good is ChatGPT at identifying that? Like vulnerable.
Source code level, it seems it's pretty good. Not only ChatGPT, there are people building customized large language models.
Yeah.
Or code large language models to do this. And there are many teams right now working on using large language models and also agents of large language models for software development. So probably it will happen soon. It's like we just need to write some description, then you will generate very good code. It can not even can generate good code, decent code, but it's not like complete code for a huge project, right? If you just ask them. Yes. Copilot can also do that. You ask it to write a function or part of the function is already pretty good. but give just the natural language spec and ask you to develop a huge program right now, you cannot do that. But I think it will happen soon. Sorry for your future. We will all be replaced one day. Yeah, so for the ChatGPT to hack this one, we have a project going on is to try to build an agent to say how good it is to hack the challenges in this class. Yeah, we're halfway there. But the students, my PhD student who is working on that is taking a break right now. That's why, yeah, he's taking one semester off. Yeah, so actually I need people to help me on that one. If you guys are interested, yeah, we can work on it. But it probably is a little bit too early for you guys, maybe after this semester. Yes. Not just use LLM, you know, use, I would say use LLM agents. So which means the LLM, the large language model plays a role kind of like a driver. You will have a list of available tools, all kind of tools, like OBJ dump, like, yes, like symbolic execution, whatever. Then we will tell large language model, this is a tool and how you use this tool, what this tool can do. And the large language model will learn like people, human, and use different tools to help you solve that problem, not just by looking at the binary or bytes here. So this is a concept called LLM agent. Yeah, Google that. I think NVIDIA has a blog on large language model agents. I didn't know this word before. We had this idea, and we think this should be a driver thing, it's large language model driver. Yeah, just recently I saw a blog from NVIDIA, and they call this is they actually have a name for this. It's an agent. Right.
I think this is
Yes. So the idea is it can actually do something, right? You just get like a binary, it can be done, but it's not a good or existing tool. If we already have a tool which is fast, which is correct, why do you deterministic? Why do you ask the large language model to do this? The large language model only needs to know, it needs to call them, so we can be fine, right? Yeah, for example, the challenge you guys had before, the integer, you need to get the integer factorization from the challenge, right? So large language model seems it's not good at that. It's not good at math at that level yet. But there are online APIs for those kind of things, right? Large language model just need to call those APIs, get the result. Yeah. That's actually how we train large language model to solve that challenge. If we give it a Wolfram API to do that, we tell, hey, the Wolfram API can do this. And you recognize this, so you call that API to get it. Yeah. Oh, by the way, I want to ask you guys about the class right before Christmas, not Christmas, Thanksgiving, right? So I think Thanksgiving is the break is Wednesday. There's a Wednesday break, I think. Email you guys. So we'll have a class before that. So you guys want to have a in-person class, or so some of you replied, say you guys are okay with online class, but I think I need to get a consensus here. So only if everyone wants to do it online, we'll do it online. Okay, everyone's happy about that? Okay, cool. Yeah, that makes my life much easier. So, because I'm commuting between Buffalo and Boston. My family is in Buffalo. So in many weeks, I have an early flight Tuesday morning. I fly in 7 o'clock, have a class 11 o'clock, then I fly back Thursday. So that will make my life much easier. So I can the week before that I can stay in Buffalo. So, yeah. Cool. Thank you very much.
The last time was also the overflow data line, overflow line.
What?
The last time was also.
Yes.
Overflow line, overflow data line.
Overflow line, not return line.
I cannot find overflow line.
Okay. Let me see. I think the TA uploaded the wrong one. They uploaded the return one. And I'm asking him to upload now. Yeah. Yes. You can have it. You cannot. The proposal of one day, part of the life over the Mhm. Yeah. The point of it, the leaders and the leaders of the country. Yeah, as long as you make something. Yeah. Very good. Very well. When you I was thinking about the, probably I was talking about the spring pointer overrun. Yeah, maybe this one. Watch the video. Too much. Yeah, we can watch the video, yeah. So far, yes, there will be some reverse engineering challenges as well. That's same several of those, right? Mhm. Okay. Mhm. Yeah. Yeah. The stakeholder is actually exactly the same stakeholder. I plan to discuss that maybe I can discuss that Fridays or the past. Yeah, just what happens is we change the compiler option a little bit. The default compiler option will make the stack frame of the main function align after any address like 16, 5. So the last 5 times 0. And then beginning you see some weird stuff with PCX, blah, blah, blah. That is trying to align the stack. So because main function is called by other functions, right? When you start, you could start any address, right? Any address could be like 1, 2, 3, 4. So that several instructions try to make it always align with 0. Yeah. That's the goal of that. Okay.
Would readers referring to the address?
Then to do that, so basically they made another stack frame there. So there were 2 copies of return address on the stack here. We probably saw that, right? Actually is in my slide. In my slides, in 2064, yeah, there's a crack me 4H, that's this version. I explained in that slide there. Okay. Then there are 2 copies of return address, but only one of them is used. I remember the one used was the second one. That's why you need to override that address instead of the original one on stack. Yeah. So that's the hard version of that. That's a default compiler option. Okay. We have an easier version to say we don't care about the stack alignment. We tell the compiler we don't care about stack alignment. Just to say some place. Yeah. In that case, the compiler will not do one of those instructions. So it will be the same as all other functions that we were familiar with.
It's nothing in the C code, it's the compiler.
No, nothing in the Seccomp. Seccomp is the same, exactly the same. Yeah.
Because I saw the C code and then this is going to get into.
You mean you decompile it?
Decompile.
You decompile it, yes. Yeah. So you can say that as even if when you decompile something, plenty of information is lost.
Right.
Those kind of detailed information, they are not related to the same.
Yeah.
Now there. Yeah, I can talk about that Friday.